Okay, this is Math 145 Notes, Section 5.3. Let's see if we can get this done. I have an 8-year-old playing right outside the door, and I live right next to a train. So good luck to us. Okay, so we are talking about independent events. Oh, so sorry about that. We are talking about independent events and what we call the multiplication rule. That will be a very important rule we're going to see in this section. Thinking about, in a 3-child family, does the first 2 children being boys make it more or less likely that the 3rd child is a boy? What do you think? Think about pulling 2 cards out of a poker deck. Does the first coming out red make it more or less likely that the second one is red too? This is the idea of independence, which we're going to talk about here today. We're also going to think about probabilities that are phrased with this phrasing at least. Like, what's the probability a 3-child family has at least 2 boys? So let's start off with the very basic definition of 2 events are independent if the event E does not affect the probability of event F. Okay? So if one occurs, or if you know one has occurred, that does not affect the probability that the other event will occur. That means they're independent. Kind of oppositely stated, 2 events are dependent if the occurrence of one does affect the probability of the other. Let's look at some examples to actually make sense of this. Number 1. I am actually going to give you a second, and actually what I want you to do is pause the video and just see, what do you think? In each of these 4 experiments that I give you, with specific events A and B listed out, which affect each other and which don't? And like I say, pause the video here, complete one, A, B, C, and D, and then play the video. So for part A, we're talking about a poker deck. Thinking about a poker deck, you have hearts, diamonds, spades, right, and clubs. Ace through king of each one of these, right? So you end up with 52 cards. 12 of them are face cards, 12 face cards. So you've got the jack, queen, and king of all suits, right? The suits being the hearts, diamonds, etc. So you get 12 face cards. Let's pull 2 decks out of a deck. Or sorry, 2 cards out of a deck. Do not replace the first card before pulling the second. So if you know event A has happened, if you know the first card is a face card, does it make event B more or less likely? Does event A happening affect the probability that event B has happened or will happen? And I would say yes, it does. It takes out a success, right? If A really did happen, then when you find the probability of B, you have one less success in the number of successes over number of possibilities, don't you? So we are going to say not independent or dependent. Okay, for letter B, let's look at this. We're rolling 2 dice. One is white, one is red, one is white. Okay, event A, the red die is 4. Event B, the white die is even. Now, it really doesn't matter what the red die is when you go to figure out the probability that the white die is even, right? The red die and the white die are totally different dice. So they're independent. One doesn't not affect the other. Excuse me. Let's do letter C. Pull 2 cards out of a deck. Replace the first card before pulling out the second. You notice how this difference of replacing the first card makes a big difference within as far as independence goes for events A and B. These are the same events, A and B, that we saw in part A of this problem. But here we replace the first card before pulling the second. Since we're replacing the first card before pulling the second card, the probability of B is not affected if you know A has occurred. So we're going to say that's independent. And then D, you roll 2 dice, one is red, one is white. A is the event, the red die is 6, B is the sum of 2 dice is 6. And I think, again, it's just helpful to think about how, if A has occurred, assume A has occurred, right? Then what's the probability of B? And in this case, think about it. If A has occurred, B cannot occur. So obviously, A occurring does affect the probability of B. So let's say these are not independent. All right, and that's page 1. All right, read over number 2, and just pause the video here and just give yourself a couple times. You're not really supposed to know the answer to the first 2 questions, by the way. We're just trying to elicit conversation. So the only idea here is that we're trying to get it in, again, independence, right? So the idea is, think about it in general. Again, you're not supposed to know the probability that a 29-year-old has high cholesterol, but think about it in general, right? Think about what is the probability that that same 29-year-old has high cholesterol if you know he eats at fast foods, right? Does the fact that he eats regularly at fast foods influence the probability that it has high cholesterol? Probably, huh? That's the general understanding, at least, about fast food. If yes, then the events are not independent. The events we're talking about are high cholesterol, and fast food, right? Again, making the idea that these are not independent. Because if you know someone eats at fast food regularly, that does in fact influence the probability that they have high cholesterol. Okay, let's look at 2B, getting at this idea of independence a little bit more as well. Again, read it and pause it. So, all right, we're selecting at random 2 29-year-olds. Does one having high cholesterol make it more likely that the second has high cholesterol? Again, we're thinking about them as random. 2 29-year-olds randomly selected from a population. They should be independents. They should be independent. 2 random 29-year-olds should be independent. One having high cholesterol should not affect the probability the other has high cholesterol. But what if we did not select them at random? What if we choose 2 men from the same family? Then they're not going to be called independent. Then we're saying, hey, probably one having high cholesterol does affect the probability that the other has high cholesterol simply because people in the same family eat in the same way, right, with the same habits. Let's look at number 3. Going to consider the experiment of example 1B, where the experiment was rolling 2 6-sided dice. One is red, one is white. Event A is the red die is 4. Event B is the white die is an even number. Let's find the probability of A. Just thinking about the red die, when I roll it, the number of possibilities is 6, and one of them is a 4. So I've got that probability. For part B, I want to find the probability of B, the white die being an even number. And again, I'm just thinking about only the white die, number of successes over number of possibilities. So let's think about this again. I'm rolling the white die. I'm picturing just the white die. Number of possibilities that could come up with just those 6 sides, right? And how many are successes? How many are even numbers? Well, my successes on the white die would be 2, 4, and 6, wouldn't they be? So that's 3 successes, or 1/2. So I've got a probability of 1/2 for the probability that the white die is an even number, and the probability that the red die is 4 is 1/6. Part C wants me to calculate P of A times P of B, which means just multiply. 1/6 times 1/2 makes 1/12. And we're going to see why that is useful on the next page. Just as a kind of a parallel thought from the last set of notes, we talked about what or means. We talked about how event E or F means E or F or possibly both. Just to be clear, we're going to talk about what and means. And means what it means in English, and. If we talk about events E and F occurring, we mean both events occur simultaneously. That is not a shocker. Okay, now we looked at 3A, 3B, 3C. Now here's 3D. And we are looking at, to tell us, or let's first off, let's say the first die is red and the second die is white. So just to be clear, every first die that you have here is red. Every second die in each pair is going to represent the white ones. Circle those outcomes, it says, that are in both events A and B. And again, A is the red die is 4. B is the white die is an even number. Okay, let's go for it. So I need the red die to be 4. So the red one is the first one, right? So it's going to be, whoops, all of those are in event A. Event B is the white die is an even number. So it's those are the white one is the second die, right? Okay, so let's see. This one, no, the white one's an odd number because it's 1, so I don't want that one. Is it 4, 2? Yeah, 4, 2 is the white die, the second die is even. Okay, 4, 3, no, I don't want that. 4, 4, yeah, that one's the white die is even. 4, 5, nope, I don't want that. And 4, 6, yeah, that one is a success, isn't it? So we have these 3 successes, don't we? So what's the probability of A and B? Is number of successes, right, over number of possibilities. I say that so much. 3 successes out of how many possibilities? Oh, that was 36, wasn't it? If you reduce it, notice you get 1 over 12, which is the exact same thing as we got when we took 1/2 times 1/6, wasn't it, earlier on the last page? This leads us to a wonderful little rule called the multiplication rule for independent events. And it says if E and F are independent events, like our A and B were up above, right? Then the probability of E and F both occurring is equal to the probability of E times the probability of F. So we can take those individual probabilities and multiply them if you know they're independent. Just like we had the addition rule for disjoint events, generalized for a whole bunch of events, we have that is true. This guy up here, this multiplication rule we had, it is true for many, many, many events, all of which are independent. So you see that from time to time. All right, this worksheet here is online. You could do it optionally, but you don't need to by any means. All right, so we're going to see some problems that have this phrase at least in them. So look at number 4 just to kind of give you an idea. Oh, where? Number C. What is the probability that at least one person chosen is right-handed? So this phrase at least is going to come up, and you're going to see that it actually is quite nice to think about them as complement problems. So to see why and how that really works out that way, let's start at the beginning of this number 4. So go ahead and read it over and pause it right here and read it over and see if you can maybe do the first couple. All right, so I have here approximately 13% of the population is left-handed. I am going to interpret that as the probability of left-handed is 13% or 0.13. And I'm using that notation. Notice P of L, meaning left-handed. So whatever notation you want to use is fine. 2 people are selected at random. Answer the following questions. Here we will assume that all people are either left or right-handed, and we're not going to worry about those ambidextrous snobs out there. Part A, probability that both people are left-handed. What I want is really what I want. I'm going to write this explicitly because I think it's important. First is left-handed and second is left-handed, meaning the first person is left-handed and the second person is left-handed. Well, wouldn't those be independent, right? Wouldn't the first person being left-handed, wouldn't that not affect the probability that the second person is left-handed? which case I'm going to get 0.13 for the probability that the first person is left-handed times 0.13 for the second person being left-handed. What is that? 0.0169, right? Let's do part B. Write out the sample space for this experiment, labeling a left-handed person as L and a right-handed person as S, or as R, excuse me. We're going to call our sample space S. All right. So I've got left, left, meaning first person's left, second person's left-handed, right? And I would get 2 right-handed people. I could have chosen a right-handed and then a left-handed, or a left-handed and then a right-handed, right? And let's put our curly set bracket. Are these equally likely? Well, we just saw that the probability of LL is 0.0169 and not 1/4, as it would be if they were all equally likely, right? So no, they're not equally likely. In fact, getting 2 left-handed people is a whole lot less common than getting 2 right-handed people. And if you think about it, left-handed people are fewer of the population, aren't they? So should be. Letter C. What's the probability that at least one person chosen is right-handed? Now, this is the reason we wrote out the sample space. So, at least one person being right-handed means they are, let's go to the sample space. Does that include the outcome LL? Is at least one person right-handed? No, it doesn't, does it? Does it include the outcome RR? Yes, it does. The outcome RR has at least one person being right-handed. Does it include the outcome RL? Why, yes, that event does include RL, and it includes LR. In fact, it includes all of the outcomes, that are not the LL. So it's a complement. So this is a complement of LL. And since we saw in the last problem, the probability, I did not leave myself much space here. The probability of the complement, I'm going to use that notation we were using. Again, that is the probability of RR or RL or LR equals 1 minus the probability of LL, which is to say 1 minus 0.0169, which is what? 0.9831. Is that how we do it? Okay, so again, we used the fact that this at least one person was right-handed was the complement of the event whose probability we found in part A. So that's really kind of handy. Now in MyMathLab, they may just ask you the question for part C, right? And so in order to do this, you will have had to do that probability that we did back in part A. So just understand that sometimes MyMathLab doesn't ask you all the little bits and pieces to lead you down the right path. They just ask you that end question at the end. So that can be a little weird. Okay. Part D, what is the probability that both people chosen are right-handed? Let's talk about this way. If the probability of being left-handed is 0.13, then what's the probability of being right-handed? That would have to be 1 minus 0.13, right? Or 0.87. So the probability of being right-handed and the second person being right-handed is the probability of being the first person being right-handed times the probability the second person is being right-handed. It's 0.87 times 0.87. And that's 0.7569. Okay, excellent. Okay, this is a pretty dang cool problem. We're talking about airline industries and their triple modular redundancy. So go ahead and read that over. In fact, maybe take a shot at number 1. Pause me down and come on back. Okay, here's my work on this one, number A. It says, assuming each component's failure or success is independent of the others, what is the probability that all three components fail? So going back to the problem, what we're dealing with is there's some component, it either fails or does not fail. If it fails, then there's a backup component. If that backup fails, then there's a backup to the backup, right? And what we're asking in letter A is what's the probability that essentially the first one fails and the second fails and the third fails. And you'll notice that this is how I wrote it with my ands written in there and of course underlined to keep them obvious. And then I say to myself, okay, well, how do I find that probability? But wait, isn't there a rule that says I can multiply these probabilities, these individual probabilities? So then I have the probability that the first fails times the probability that the second fails times the probability that the third fails. And that's 0.006 times itself 3 times, which is 0.006 cubed. I put that into my calculator. Now, technically, my calculator actually gave me 2.16 e negative 7, which you've got to be aware that that's the way that your calculator, right, scientific notation. What I did to interpret that is I took the 2.16 and that decimal place, which was in between the 2 and the 1, I moved it to the left 7 places and then filled in zeros, and you'll see that that's what I ended up with up here. So not only did we need to use our multiplication rule, but we also needed to deal with scientific notation on the old calculator. So that's very interesting. Why don't you pause me down and do B, and then we'll look at C also together. Okay, so for part B, I was trying to find and mark the event considered in part A, which was the event that the components all three fail. And so I noticed that that's along that branch of the tree diagram. And there's my FFF, fail, fail, fail. And so that's for part A. And again, you'll notice how those 0.006s along the tree diagram could have simply been taken, multiplied together to get the probability of FFF. So that's good. Now, let's look at C. What is the probability at least one of the components does not fail? Then it asks me to find and mark the events considered here. In fact, let me find and mark those events. Oh, actually, those are outcomes. Come to think of it, that is the wrong word there. Those are actually outcomes. Find and mark the outcomes considered here. Well, I want at least one component not failing. Oh, by the way, I did use the complement notation that we saw earlier in the notes. I think it was in section 5.2 that they showed me the complement of F, which means component does not fail. Now, we had already seen that the probability of complement is 1 minus the probability of the event. So I'm just taking 1 minus 0.006 to get that 0.994 that you see there throughout for the probability that a component does not fail. Okay, now that being said, let's go find and mark the outcomes considered in part C, which again is the outcomes where at least one of the components does not fail. So I want at least one FC. And you'll notice very simply that they're all of these. Look through there. You're going to see at least one failure on each one of those 7 outcomes. And so, and this is kind of the point of these at least probability questions. And so I can find this probability by taking the probability we found in part A and simply subtracting it from 1. Why don't you pause me down and take a shot at writing that notation down and then, of course, doing that calculation and seeing what your answer is. Pause me down. Meet me back here. All right, here's my answer. And again, the notation is almost as important. I have the probability at least one component does not fail. So that is because it's a complement of the event in part A, I'm going to say it's equal to 1 minus the probability that they all three fail. And again, this is the probability that we found in part A. So I take 1 minus 0.00000216, and that got me this crazy number. So essentially, this is the probability that the plane will land safely, isn't it? Darn near 100%, which is a really good thing for all of us plane travelers. All right, let's see what else we got. Okay, why don't you read over number 6 and try letter A, and if you want to, why don't you go ahead and do B as well. Pause me down and come on back. Okay, I'm going to talk through letter A and B here. Letter A, I've got the probability that she makes 3 free throws in a row is the probability that she makes the first and makes the second and makes the third. Because they are independent, and that was told to us in the setup of the problem, I can say I'm going to use my multiplication rule and just multiply the probabilities of her making the first, her making the second, and her making the third. And each of those are 64%. So I have 0.64 cubed, and that was 0.26. I did have to round it. Make sure, again, if you're rounding your answers, you put an approximately equal sign there just to remind yourself that you actually rounded it. Always a good idea. On letter B, it says, what's the probability, that Eliza makes 3 free throws in a row, but does not make 4 in a row, which is to say she make, and then misses. All right, so that's the probability that she makes the first and makes the second and makes the third and misses the fourth. So remember, to find the probability that she misses, well, that's 1 minus the probability that she makes it. And so that is why I got 0.36 in that spot. Again, because of these independence between events, I can say I can multiply those probabilities, and I do that. And of course, I'm rounding it, and I got 0.09. Let's have you take a look at letter C. Pause me down, try it out. Notice it's an at least probability. So, all right, for part C, once again, I'm talking about the probability of something at least blah, blah, blah. And so I can think about that as a complement. In my thought bubble over here on the left-hand side, I wrote the 8 possibilities. By the way, this is very, very similar to the 8 possibilities that came out from the airline triple modular redundancy application as well, you'll notice. Because there was 3 parts and each part had 2 options, right? Fail or not fail for the airline problem. Here we have make the free throw and not make the free throw. So it's very, very similar. Now, I have those possibilities because, again, the make was the probability we found in part A. If I want to know the probability that she misses at least one, you will notice that all of the other ones here, all of those other outcomes that are possible, are what we're looking for in part C. So I am going to say to myself, the probability of missing at least one is 1 minus the probability that she makes all 3. You'll notice I used the exact form of that probability, not the rounded version 0.26, but I used the exact form 0.262144. And I subtracted that from 1 and I got the accurate, notice it's equal sign. I did not round this 0.737856, but then I did later on round it to 0.74. So I used the approximately sign there. I also just want to kind of think about that as a percentage. Well, that's 74%. So what I'm saying is, of all the times she has a 3 attempt string, it's the probability that she misses at least one will be 74%. So 3 out of 4 times, when she tries for those 3 attempts, she'll miss at least one. All right, good to know. Here is a worksheet that I think would be very useful for you to do. Go ahead and ask me questions about it if you would like. And let's wrap that page up. All right, this is number 7, and this we're talking about the connection between actual statistical data, like gotten from a survey, and our rules that we've developed. In particular, we're thinking about the one that says if two events are independent, then the probability that they both occur equals the product of each probability separately. Okay, so let's get started. Read over, of course, that, and then think about parts A, B, and C. Pause me down and come back. All right, so first of all, I took my data from my sentence, the setup there. It said only 14% of adults in a country bet on professional sports, and so I made that the probability of bets equals 0.14, and then it also says that 45.8% of the adult population is male, and so I have that probability of being male. Again, both in decimal form. And then part A says, are the events male and bets on professional sports mutually exclusive? And I said, no, certainly they can happen at the same time. There are definitely men who bet on sports, and so they are not mutually exclusive. In part B, it says, assuming that betting is independent of gender, compute the probability that an adult from this country selected at random is male and bets on sports. So, in my shorthand notation, I have probability of male and bets. Because they're independent, I can multiply those two probabilities, and I end up with 0.458 times 0.14, which gets me 0.06412. I decided not to round that at all, but I did then round it, I guess, when I wrote it in percent form over there. So, according to our data so far, 6.4% of the country are people who are male and bet on professional sports. All right, now let's do C. Using the result in part B, compute the probability that an adult selected at random is male or bets on sports. All right, so here is my starting off point. And I have a formula for that comes from 5.2, doesn't it? And so I know the probability of male or bets is the probability of being male plus the probability of being a better minus the probability of male and bets, or their intersection. And I put all those numbers in there. I got 0.53388, which again, just putting it in percent form gives me that. Now, here is kind of an interesting idea going on here, and this is D and E kind of are linked together. It says D, the poll data indicated that 8.3% of adults in this country are male and bet on sports. What does that indicate about the assumption in part B? The assumption that we used to make that answer up there. So pause me down, think about that, and come back. All right, so it says on part D that poll data actually indicates 8.3% of the adults are male and bet on sports. It goes on to ask me, what does this indicate about our assumption in part B? And again, going up there, we are assuming that betting is independent of gender. So let's look at that. Back down here on what I wrote for D. It says, when we assumed male and bets were independent, we got the probability of male and bets at 6.4%. But survey data says it's really 8.3%. So since we did not get the same number as when we made that assumption and versus the survey data, we know our assumption of independence is wrong. Gender and betting are in fact not independent after all. That's what that means, right? So not only can we use this rule to say if two events are independent, then you can multiply their probabilities to figure out the probability that they both occur, right? But the way we're using it here is kind of backwards from that, isn't it? We're saying if you can show that the probability of being male and Bets is equal to the probability of male times probability of Bets, then you can say that the two events are independent. We can't show that here, though. These are not the same. Therefore, gender and betting are not independent. We're going to use that on letter E to basically recalculate the probability that we had found in part C. All right, so when I did that, of course, I laid down my generic probability of male or Bets. I'm using my formula that says it's the probability of male plus the probability of Bets minus the probability of male and Bets. But in this case, I'm going to subtract off the survey data, 0.083, and that, of course, is just my 8.3% that the survey data told me. And in that case, I get exactly 0.515, which tells me 51.5% of the population is male or Bets, as opposed to the 53.4% that we would have gotten under that erroneous assumption. All right, so that wraps up that page, and of course that wraps up the 5-3 notes. So if you have any questions, don't forget that I'm out here. Shout out to me. I'm happy to answer. Bye.